This video is for everyone who truly wants to understand how solar panels turn sunlight into electricity. If you're just curious, you can leave. Most people see solar panels as simple black rectangles on rooftops, but behind them lies an entire chain of physics, material science, chemistry, and industrial engineering that begins with something we've spent our lives ignoring. A material so ordinary we treat it like dirt. A material within which lies the potential to turn a burning summer sun into clean and pure electricity. Sand. How solar panels really works, from sun to electricity. What is the physics behind solar energy conversion? How silicon becomes an electrical material and how sunlight is transformed into usable electricity. This is exactly what you're going to learn in this video. My name is Ken, you're watching The African Grid. Let's begin with the very foundation of the process. Silicon begins as sand, mainly rich in quartz. But not all sand works. Only specific deposits with high silicon dioxide concentrations are useful for industrial silicon production. These are found in regions with high purity quartz sources such as certain beaches, sandstone formations, and desert dune systems around the world. The first stage is mechanical and chemical purification. The raw material here is washed and processed to remove organic materials, clay, dust, and unwanted minerals. And what remains is a concentrated form of silicon dioxide, which is in fact the true starting material for modern photovoltaic technology. Next comes one of the most energy-intensive stages of the entire manufacturing chain. The material is heated inside industrial furnaces at a temperature of roughly 14 to 2000 degrees Celsius. At this stage, silicon dioxide is chemically reduced. A reduction reaction is a reaction in which an atom gains electrons. In this case, the silicon inside SiO2 is separated from oxygen using carbon. Here's the simplified reaction. The result is the production of raw metallurgical grade silicon. By metallurgical grade silicon, you should understand a silicon that is typically around 98 to 99.5% pure. However, it still contains some impurity, such as iron, aluminum, boron, and other traces of contaminants. And for solar panel manufacturing, this level of purity is still far from sufficient. Inside a solar cell, electrons must move through a crystal structure with minimal resistance and minimal recombination losses. Impurity disturbs this movement. That creates defects inside the semiconductor and increases therefore the probability that electrons get recombined before contributing to electrical current. This is why the silicon must undergo a second and much more advanced purification process. The metallurgical grade silicon is first crushed into smaller fragments. It's then reacted with high hydrogen chloride gas at high temperature, producing silicon containing compounds such as trichlorosilane. This step is extremely important because once silicon is transformed into a gaseous compound, it becomes possible to purify it much more efficiently through fractional distillation. Distillation works because different chemical substances have different boiling points. As temperature changes inside distillation columns, some compounds vaporize earlier, other compounds later. This allows impurities such as boron, phosphorus, and metallic contaminants to be progressively separated from the silicon-containing gas. After multiple purification stages, an ultra-pure silicon-containing gas is obtained. But solar panels cannot be manufactured from gas, so the purified silicon compound must be transformed back into solid silicon, and this is commonly achieved through the Siemens Process. Before going further, it is important to understand that the photovoltaic industry is extremely large and technologically diverse. The process presented in this video does not include every single industrial variation or intermediary manufacturing step used worldwide. Instead, it focuses on the dominant industrial pathway and the most fundamental physical and engineering principles behind monocrystalline silicon solar panels. Some manufacturing lines may use additional optimization steps, different chemical treatments, alternative cell architectures, and different production techniques. But once you understand the process shown here, you will possess the core scientific foundation required to understand how much modern solar panels are manufactured and how they operate physically. Let's come back to the Siemens process. In this process, purified trichlorosilane gas decomposes at high temperature onto heated silicon rods. As the gas decomposes, pure silicon atoms deposit onto the rods, layer by layer. And only at this level does silicon become suitable for high-performance photovoltaic and semiconductor applications. At this point, the material is no longer ordinary industrial silicon. It has become one of the purest engineered materials ever produced at industrial scale. and only now can the crystal formation process truly begin. Here, manufacturers must choose between two different crystal structures. The first is polycrystalline silicon. This is a cheaper and simpler process where molten silicon is cooled directly inside molds. The result is a material composed of multiple crystal grains, oriented in different directions. As you can see, this method is cheaper, requires less energy and process control, but it produces a silicon with a very low efficiency. The second option is monocrystalline silicon. This is the dominant technology used in most modern high-efficiency solar panels today. This allows the electrons to move much more freely through the materials with just few structural interruptions. This is why in this video we will focus mainly on monocrystalline silicon and the process used to manufacture it. In order to create monocrystalline silicon, the ultra-pure polysilicon produced during the Siemens Purification process is melted once again inside a quartz crucible. This occurs at temperatures around 1414 degrees Celsius, which is the melting temperature of silicon. Inside the furnace, the silicon becomes fully molten. The temperature is controlled with extreme precision and the environment is carefully isolated to avoid contaminations. And this is where one of the most remarkable processes in the modern materials engineering truly begins. A very small crystal called a seed crystal is slowly lowered into the molten silicon. This seed crystal already possesses a perfectly ordered atomic arrangement. As it touches the molten silicon, atoms from the liquid begins attaching themselves to the seed crystal structure. This seed crystal already has a perfectly ordered atomic arrangement. The seed crystal is then slowly rotated and slowly pulled upward, typically at speeds of only 1 to 3 mm per minute. This controlled extraction gives silicon atoms enough time to organize themselves into exactly the same orientation as the seed crystal. Instead of random crystal formation, the atoms align into one continuous crystal lattice extending through the entire ingot. The process is intentionally slow because crystal perfection is critical. If growth occurs too quickly, defects appear, atomic alignment breaks, internal stresses form, and efficiency decreases. Here, the objective is not speed. The objective is atomic order, and after many hours and sometimes many days depending on the ingot size, the result is a massive monocrystalline silicon ingot. Modern ingots can reach diameters to 150 to 300 mm, length of 1 to 2 meters, and masses exceeding hundreds of kilograms. The characteristic cylindrical shape comes directly from the rotational pooling process itself. After the purification, extremely small residual impurities still exist inside the molten silicon. But many of these atoms do not integrate very easily into the perfectly ordered crystal lattice. As the ingot slowly grows, the crystal tends to reject part of these impurity atoms, which remains inside the molten silicon and then progressively get accumulated near to the final portion of the melt. This is why the impurity concentration becomes much higher near the tail end of the ingot. And for that reason, these regions are often removed or processed separately in order to preserve the highest purity material. But why are monocrystalline cells more efficient? The final monocrystalline structure contains far fewer grain boundaries compared to polycrystalline silicon, and this matters enormously. In polycrystalline materials, electrons encounter interruptions between crystal grains, but in monocrystalline silicon, the crystal lattice remains continuous, electrons' mobility improves, and carrier lifetime improves too, and this all improves photovoltaic efficiency. At this point, the silicon is no longer a simply purified material. It has become a perfectly engineered semiconductor crystal designed atom by atom to control the movement of electrons. And only now can the giant crystal be transformed into thin wafers that will eventually become solar cells. The ingot is sliced using a high-precision diamond wire saw. These wires are extremely thin, typically around 100 to 200 micrometer in diameter. The goal is to minimize silicon loss while maintaining extremely precision cuts. The resulting wafers are usually around 150 and 200 micrometer thick. This is actually thinner than in human hair, but despite this fragility, the wafers will then become the active semiconductors platform for the solar cell. Here's an important fact. Because the original ingot is cylindrical, the first wafers are naturally circular. However, circular cells waste valuable place inside solar modules. In order to improve the packing density and maximize active surface area, manufacturers trim the wafer's edges into square or pseudo-square geometries. Now begins one of the most important stages of the entire manufacturing process, the creation of the p-n junction. It's the region that allows sunlight to become electrical current. Modern monocrystalline solar wafers are usually manufactured either as p-type silicon or n-type silicon, and this depends on the cell architectures. But historically, most commercial solar cells use p-type wafers doped with boron. This is called doping, and here is how it works. Silicon atoms normally forms 4 covalent bonds. Boron, however, has only 3 valence electrons. When boron replaces silicon atoms inside the crystal lattice, 1 electron bond remains incomplete. This absence behaves like a positive charge carrier called a hole. The opposite is true for phosphorus atoms, which contain 5 valence electrons. So after this doping process, when phosphorus replaces silicon atoms inside the crystal lattice, 1 electron remains free and can move through the structure. This is called n-type doping. In order to create the p-n junction, manufacturers introduce a very thin n-type region near the surface of the wafer. This is typically done using phosphorus diffusion. The wafer is exposed to phosphorus-containing gases inside high-temperature furnace. At elevated temperatures, phosphorus atoms diffuses only a very short distance into the silicon surface. The diffusion dip is extremely small, typically on the order of 0.1 to 1 micrometer. These create a very thin n-type emitter layer on top of the p-type substrate. The process described here is known as the thermal diffusion, which remains one of the most widely used industrial methods for forming doped regions in photovoltaic manufacturing. In this technique, as described earlier, wafers are exposed to phosphorus-containing gases at high temperature, allowing phosphorus atoms to slowly diffuse into the silicon surface. Another advanced technique also exists, called ion implantation. Instead of relying on thermal diffusion alone, ion implantation accelerates dopant ion using electromagnetic fields to physically embed them into the silicon crystal with extremely high precision. Ion implantation is widely used in advanced semiconductor manufacturing and is increasingly being explored in high-efficiency photovoltaic technologies because it allows much finer control over dopant concentration and junction depth. When the p-type and the n-type regions come in contact, charge carriers begin diffusing across the boundaries. Electrons move toward the p-type and holes move toward the n-type. This diffusion creates a region depleted of free carriers called a depletion region, and inside of this region, an internal electric field naturally appears. This electric field is the mechanism that allows the solar cell to function. When photons from sunlight strike the silicon surface, they transfer their energy to electrons inside the crystal lattice. But not all photons can do this. The photon must contain enough energy to overcome the silicon band gap. If the energy is sufficient, an electron is excited and freed from his atomic bond. Electron-hole pairs are generated. Without the electric field, this carrier will rapidly recombine, but the internal field separates them almost immediately. Electrons are pushed toward one side and holes toward the other. At this stage, the solar cell is finally capable of interacting with sunlight. Before the electrical current can be efficiently extracted, another major problem must be solved: the reflection. In fact, a bare silicon reflects a significant portion of incoming light. In order to reduce these optical losses, manufacturers deposit an ultra-thin anti-reflection coating, which is commonly made from silicon nitride. This layer reduces reflection, traps more light inside the cell, and increases therefore the photon absorption. The characteristic dark blue or black appearance of modern solar cells comes largely from this coating. Now, the generated electric current must be collected and extracted from the cell. In theory, the easiest solution will be to fully cover the surface with metal, but this will block the sunlight from entering the silicon. So engineers must solve the compromise: collect as much electricity as possible while blocking as little light as possible. To achieve this, extremely thin metallic lines called fingers are printed onto the front surface of the cell. These fingers collect electrons generated near the surface, minimize resistance losses, while shading only a small fraction of incoming light. The collected electrons are then transferred into thicker conductors called busbars. These busbars gather current from all fingers and channel it toward the external electrical circuit. Once extracted from the contact, electrons travel through an external circuit, and this is the usable electrical current capable of powering devices, batteries, and electrical grids. And after passing through the external load, these electrons return in the backside of the cell, where the recombination with holes occurs. After the metallic contacts are deposed, the cells now undergo a high-temperature firing process. It improves electrical conductivity and also reduces the contact resistance. After this process, each solar cell is then electrically characterized and tested. Manufacturers measure voltage, current output, conversion efficiency, and defect levels. The cells are then sorted into performance categories to ensure uniform electrical behavior inside the final module. Now they are interconnected to form a complete photovoltaic module. The final electrical architecture depends on the desired module specifications. The interconnected cells are then encapsulated between multiple protective layers: tempered glass on the front surface, polymer encapsulation layers. These layers protect the cells from moisture, oxygen, UV radiation, and mechanical stress, while still allowing maximal light transmission. At the back of the module, a junction box is installed. These components serve several critical functions: connects and routes electrical output, prevents moisture intrusion, and hoses bypass diodes. The bypass diodes are especially important. If part of the panel becomes shaded, these diodes allow current to bypass affected sections, reducing overheating and preventing power losses. The process explained in this video represents the dominant industrial pathway used in modern crystalline silicon solar panels today. But the photovoltaic industry contains many other technologies and architectures designed to improve efficiency, reduce cost, and adapt solar cells to different applications. At the material level, alternative solutions also exist, including perovskite solar cells, gallium arsenide solar cells, cadmium telluride technologies, and CIGS thin film cells. All of them rely on the same fundamental principle: using semiconductor materials to absorb photons and generate electrical charge carriers. What changes is mainly the material itself, the current structure, the manufacturing process, and the resulting efficiency. Inside technology itself, there are also multiple modern architectures such as PERC, TOPCon, HGT, and IBC cells. These designs optimize charge extraction, surface passivation, recombination reduction, and overall efficiency. At the module level, systems can also be configured as monofacial panels or bifacial panels capable of collecting light from both sides. Despite all these innovations, crystalline silicon remains dominant globally because of its balance between abundance, stability, mature manufacturing infrastructure, and large-scale industrial scalability. In fact, what appears externally as a simple dark panel is in reality a multi-layered engineered system integrating semiconductor physics, optical engineering, precision manufacturing, thermal management, and electrical power conversion, all operating together to transform sunlight into usable electricity through controlled physical processes. Some industrial footage and educational manufacturing visualizations used in this video were sourced from pvmanufacturing.org. Special thanks to the platform and contributors for supporting open technical education in photovoltaic manufacturing. When considering this technology at scale, one question becomes central: what will it mean for a continent such as Africa, rich in solar resources and raw materials, to fully develop and integrate such an industry? And beyond energy generation, how might silicon-based semiconductor technologies, fundamental to solar cells, electronics, and modern computation, continue to shape global development across the coming decades? The comment section is yours.